Hello everyone, welcome to this particular lecture of Unit 4. Today we will discuss about optocouplers and liquid crystal display, in short LCD. So what is an optocoupler? An optocoupler, it is also known as optoisolator or photocoupler or optical isolator. It is a semiconductor device that will transfer the electrical signal between the two isolated circuits by using the light. And this optocoupler, it will prevent the high voltages from affecting the system receiving the signal. So there are two parts that are used in optocoupler. At the input side or transmitting side, we have an LED. Okay. So when you give the electric supply to the LED, we know LED will convert the electricity to light. This is an infrared LED. So this will convert the electricity to the infrared light. We know the wavelength of the infrared light is between 700 nanometer to 1 millimeter, and the infrared frequency is very high, around 300 gigahertz to 400 terahertz. So we can't actually observe this infrared light in our bare eyes. So when at the transmitting side, at the transmitter side, when you are giving the electric supply to this infrared LED, it will emit the infrared light, and the receiver side we have a photosensitive device. So as a photosensitive device, we are using the phototransistor. So when this infrared light it hits the base, this phototransistor can be NPN type or PNP type. So when this infrared light it hits at the base of this phototransistor will convert the light energy to the electrical energy. Okay, so this is how this optocoupler circuit works. But in that case, in case like if LED is not emitting the infrared light, that means when we are not giving any electric supply, when the LED is not able to emit the infrared light, in that case the phototransistor at the receiver side will remain off. So the input circuit takes the incoming signal. This input side, this electrical signal can be AC or DC type, which will be used to turn on the LED. And LED will emit the infrared light, which will give that required base supply to the phototransistor at the receiver side, and the phototransistor will convert that light energy back to the electrical energy. So we can have different kinds of arrangements for optocoupler. So in this optocoupler transmitter side, we have this LED. So these different arrangements of the optocouplers are based on the variation in the receiver side. You can see for all these four arrangements, the transmitter side LED is fixed, and transmitter side we are giving the electrical supply to the LED. But in the receiver side, you can see here we are using the phototransistor at the as the receiver. In this diagram, we are using a Darlington pair. That means here we have the two BJTs, both are NPN type. The emitter of the first BJT is going to the base of the second BJT. So the reason for using this Darlington pair at the receiver side, because this kind of pair in the receiver side it will produce more gain. We will get more electrical output signal. These two arrows, that means the light radiation. In the third configuration, it is a SCR. So at the receiver side, we are using the SCR. We have already covered the SCR topic, which is the silicon controlled rectifier. So here, the infrared light that is emitting from this LED, it acts as a trigger signal to the SCR. Okay. Here also this SCR at the receiver side, it will generate the electrical output signal. Next, here we are using at the receiver side triac. Triac is triode for alternating current. The full form of triac is triode for alternating current. Here at the receiver side, two SCRs are connected back to back, and these SCRs are getting their required trigger supply from this infrared LED, and it will convert that light energy to the electrical energy. Now, these optocouplers can effectively remove the electrical noise from signals. They can isolate the low voltage devices from the high voltage circuits. The device is able to avoid disruptions from voltage surges. Voltage surge means whenever there is a very high value of voltage. Example, radio frequency transmission. We know the radio frequency transmission occurs at very high frequency range in the order of megahertz or gigahertz range. Then lightning strikes, spikes in a power supply, etc. These optocouplers, they also allow the usage of small digital circuits to control the larger AC voltages. So our next topic of discussion is liquid crystal display, or in short LCD. So this operation of LCD, it is based on the polarization of light. We know light wave, it is an electromagnetic wave which consists of both the electric field and magnetic field perpendicular to each other and perpendicular to the direction of the light wave propagation. Now, what is a polarized light wave and what is an unpolarized light wave? When the electric field vector variations, they occur just randomly at different planes. When the electric field vibrations, they occur at different planes, we call it as unpolarized light wave. When the electric field vibrations, they occur at a particular plane, at a particular direction, we will call it as a polarized light wave. You can see here in this arrangement, these light waves, you can see the vibrations, they are not directed to a particular plane. They have random vibrations. So when these unpolarized light waves, these are called unpolarized light wave, when they are allowed to pass to a polarizer, you can see at the center of the polarizer there is a dotted line. This is called the crystallographic axis of the polarizer. So when these unpolarized light waves, they are allowed to pass to the polarizer, so the light waves that match the crystallographic axis of the polarizer, only those light waves will be coming out from the polarizer, and these light waves are called the polarized light waves, because here the vibrations, they are directed at a particular direction, at a particular plane, and they are, you can see, these vibrations that are coming out from this polarizer, they are parallel to the crystallographic axis. Okay, so these vibrations, we will call it as a polarized light wave. Okay, and we also know, as I already told, that light wave, it is a combination of the electric field vector and the magnetic field vector. So the magnetic field vector is the vertical component of the light wave, and the electric field vector is the horizontal component of the light wave. That means this magnetic field vector, it acts perpendicular to the horizontal electric field vector. Now, so I told here we had the unpolarized light wave. When I am passing through it the polarizer 1, the vibrations that are parallel to the crystallographic axis of this first polarizer, only those vibrations will be coming out, and we are calling it as polarized light wave. Now we have a second polarizer over here. Okay, now what the second polarizer will do, this by controlling the rotation of this crystallographic axis of the second polarizer, we can control the intensity of the light. Okay, so you can see as we are moving this polarizer to the crystallographic axis of the second polarizer is getting changed, and accordingly our intensity will change. So the first polarizer will help to get the polarized light wave, and second polarizer will help us to control the intensity of the polarized light waves. Okay. Now, when the vibration it is perpendicular to the crystallographic axis of the second polarizer, then the intensity of the light coming out from the polarizer 2 will be 0. So, what is liquid crystal? Liquid, in the liquid crystal LCD, the liquid, we have the liquid crystal molecules. So these liquid crystal molecules, they are in the state between the solid or crystal and the liquid state. Okay, so in the liquid crystal display, we have an arrangement of the liquid crystal molecules. Now, let's say this is my liquid crystal thin film, which is made up of several liquid crystal molecules. Okay. Now, when an light is incident on this, you can see the light is coming from the back side, and here the light is coming out from this liquid crystal thin film. Now, if somehow we can manipulate the arrangement of the liquid crystal molecules in this liquid crystal thin film, then we can control the intensity of the light that is coming out from this LCD. Okay. Now the question is how we can manipulate how we can manipulate the orientation of these liquid crystal molecules. We can do that by applying a small electric field or magnetic field at different regions, at different small regions of this liquid crystal display. So, if we can apply a small electric field or magnetic field at different small regions of this liquid crystal display, we can manipulate the orientation of the liquid crystal molecules. Thus, we can control the intensity of the light. Okay. Now, if we can divide entire this liquid crystal display into small regions, each of these small region is called a pixel. So higher the number of pixels per unit area, higher will be the resolution of your image, higher will be the and clearer the image will be. Okay. What I mean is, in the liquid crystal display, the entire display it is made up of many small square boxes. So each of these square boxes height wise, and this x axis and y axis, we have these small boxes. Now if each of these small boxes is called the pixel, and if we can zoom this small box, it is not a blue, it consists of three different colors. This is a red, this is green, and this is blue color. Okay. So as I told, if we can increase the number of pixels per unit area, then, and if we can apply the electric field or magnetic field to manipulate the orientation of the liquid crystal molecules, we can control the intensity of the light. And as the number of pixels per unit area is increasing, higher will be the resolution and clearer will be the image. You can see here the number of pixels per unit area is very low, so lower resolution. Okay, here lower resolution, and here this resolution is somewhat improved, and here it is more improved than this one, and it is of high resolution. Okay. Now if we look at the arrangement of the liquid crystal display, so let us start from this right side to the left side. So first we have a case. This case is there to protect the entire arrangement from the external damage. Then we have this backlight. This backlight emits the white light. Okay, and this white light, it falls on this backlight emits a white light, and then this backlight, it is allowed to pass through a polarizing filter. Okay, so this polarizing filter is a vertical polarizing filter. Okay, this backlight, it consists of the unpolarized light wave. So when it is allowed to pass through the polarizing filter, what will happen? Only the vertical vibrations will come out. Okay, only the vertical components of the light will come out. We will get the vertically polarized light wave. So when those vertically polarized light wave, it falls on this liquid crystal thin film, then if I want to control the intensity of the light coming out from this liquid crystal thin film, what I need to do? I need to manipulate the orientation of the liquid crystal molecules over here. Okay, and that how can we do? For that we have this TFT matrix or thin film transistor matrix. It will provide the required electric field or magnetic field to manipulate the orientation of the liquid crystal molecules in this thin film, and as a result we can control the intensity of the light coming out from the liquid crystal display. Okay, now in this liquid crystal thin film, what it can do, we have given the vertically polarized light wave. So what this liquid crystal thin film will do, it will twist it at 90 degree and it will make it the horizontal light waves. Okay, it will make those vertical vibrations of light, which are polarized light wave, to the horizontal vibrations. And I already told how can we control the intensity of the light by controlling the orientation of the liquid crystal molecules. How we can control the orientation of the LCD molecules? By applying the electric field or magnetic field at small regions of this liquid crystal display. Okay, now that but now this horizontally polarized light wave, it is allowed to pass through a color filter. Okay, now since we already have this horizontally polarized light wave, it is allowed to pass through the horizontal polarizing filter. So obviously it will be easily able to pass through the horizontal polarizing filter and we will get a colored image on screen. Now let's say for example you want some portions black in the screen. In that case, what it will do? So up to this step it is same. That means you are giving the backlight, which is a white light, and it is an unpolarized light wave. First it is allowed to pass to the vertical polarizing filter and only the vertical component of the light is coming out. Then it is falling on the liquid crystal thin film, and in this case here in this liquid crystal thin film, it is, let's consider it is sandwiched between two electrodes. One is positive electrode, one is negative electrode, and these electrodes are glass electrodes. We can make these electrodes conductive by having a coating of ITO or indium tin oxide. So if we can apply a potential between these two electrodes, in that case previously this liquid crystal was twisting that vertically polarized light wave at 90 degree and making it a horizontally polarized light wave. So if we are applying that potential between the two electrodes, this LCD won't be able to do that anymore. Okay, that means it won't be able to convert that vertically polarized light wave to the horizontally polarized light wave. So until and unless the light is converted to the horizontally polarized light wave, there is no chance that it will be allowed to pass through the polarizing filter. Okay, so in those portions on the screen we will get the black. So this is how a liquid crystal display works.